Now in this video I will show you how to operate a light-dependent resistor, an LDR, in a measuring bridge in such a way that we can use an operational amplifier in a comparator mode, which is something which we have looked at in the last video, to switch on a light-emitting diode, and this should depend, if it's set up correctly, on the light intensity. So below a certain light intensity I want the LED to be switched on, otherwise I would like it to remain switched off. In order to get there, firstly I'll briefly explain how a light-dependent resistor works. We will quickly repeat what operational amplifier and comparators are, and then we'll start with the actual experiment. Now let's first look at the light-dependent resistor. Here you can see such a device, and the goal of this the circuit which we are about to build is to measure the ambient brightness using such a component. And here in this diagram we can see the characteristic curve of this resistor here, the resistance value here on the y-axis and the ambient light level measured in lux on the x-axis. And for example, for this setting here, 10 lux, which corresponds to roughly a dimly lit street using only street light falling onto the street, this is roughly 10 lux, and for this value we get a value of resistance value of roughly 10 kilo ohms. And this measuring circuit, which is something which we have already tried out in the first experiment, simply divides up the voltage provided by a battery, a 9-volt battery. This is the internal resistance of the battery, across two resistors, a reference resistor, 5K, and this LDR. And you can see that in accordance with the voltage divider law, the voltage drops are split up equally according to the respective light levels or the respective resistance values across these two resistors. For 10 lux we have 10 kilo ohms, and this resistor has 5 kilo ohms, so it makes sense that the 10K resistor has double the voltage drop than the 5K resistor. So it's a very simple voltage divider setup, which you can see here for this LDR circuit. Now let's take a look at the first experiment. What we want to do now is we want to adjust a potentiometer in such a way that the operating voltage is divided between two components in a ratio of approximately 1:1. So this is a very simple operating mode of the potentiometer. We're going to use other more sophisticated operating modes in upcoming videos, but in this case we're going to use this potentiometer as an adjustable resistor. We're going to connect these two pins, the leftmost and the middle one, and then turn the knob and adjust the resistance value between these two pins between 0 volts, which is leftmost, and between, I think, the 10K resistor, between 10K, which is the rightmost setting of this potentiometer. The question is, which we should try to answer, is which 2 points in the circuit should then be compared by the operational amplifier. Let's try to find a way which generates a signal which is proportional to the resistance of this light-dependent resistor here, this LDR. What you can see here, this circuit is a series connection of the LDR and a potentiometer, which we already have talked about in another video. And this potentiometer basically divides the voltage between its connectors. Let's take a brief look here at how it looks. It has 3 connectors, and these 3 connectors have a fixed resistance between the outer, between the first and the last connector. This particular potentiometer has a resistance value of 10 kilo ohms between these two pins here, and the middle pin, this is a variable resistor value here, which you find, and it divides the resistance up between the first and the middle one, and the middle one and the last one. So if this knob here is turned to the left, the resistance value between these two connector pins here is 0. If you turn it to the full right, the resistance value between these two pins is the maximum resistance value of the potentiometer, which is 10 kilo ohms. So we can adjust the resistance value between these two pins here by turning the knob, which is what we are going to use it for here in this experiment. And the idea is to divide up the voltage of this battery here, 9 volts, between the LDR and the potentiometer. So we can generate a voltage which we can evaluate using the comparator and the operational, which is the operational amplifier, which we have talked about in another video. Now let's fire up this multimeter here, this measurement device for voltage, and let's connect it to 2 points in the circuit. The first point is going to be the base or the negative terminal of the battery, this one here, and the other point which we're going to look at is the point in between the LDR and the potentiometer. Now let's connect this pin there, and now let's fix both the pins to this to these connectors here. And what you can see in the display here, let's activate this. What you can see on the display here is a voltage drop of 4.8 volts across the potentiometer. And when I turn the knob, you can see that the value changes. If I turn it to the full left, just as predicted, it has a voltage of approximately 0.02 volts. And if I turn it to the full right, the voltage drop is approaching 7.3 volts. It's the full 10 kilo ohms now. And all the values in between, this means, based on the resistance value between the two pins, that the voltage is divided up between the potentiometer and the LDR. And if I put my finger across the above the LDR, you can see that the value changes again. And now we have a stable, it's not stable, but we have a voltage which we can use to trigger, let's say, a switch, a digital switch, which is used to light up an LED based on the voltage drop across the potentiometer, and which is dependent on the level of ambient light. Now it's 3.5 volts roughly, and if I take my finger away, it's approaching 6.6 volts. The problem which we are still facing here is that we have no way of generating a second signal, because if you recall the video on the comparator, the basic idea behind it is that we generate two signals which are approximately the same size in a situation where we want to use one as the reference for the other. So this means that in order to have a 0 voltage difference on the entrance of the operational amplifier, what we need to do is we need to generate a voltage drop somewhere on this board here, which we can use as a reference voltage for the second input pin of the operational amplifier. We'll get to the OPV in just a few minutes, but now let's insert two more resistors into this breadboard here, two equal identical resistors, both 10 kilo ohms. And if I enter them in just this manner here, they are connected across the divider gap by this black bridge here. And what you can see now is that the voltage of the battery is divided equally between these two here. If I place the measurement pins once more into this setup here, let's find a place where we can do this. Let's use this red cable and connect the negative terminal of the voltage measurement device here again to mass, to the negative terminal of the battery, and the red pin or the red connector to this red cable here. And as you can see, we have a voltage signal of 4.061 volts. And what we need to do now is we need to adjust the potentiometer in such a way that the voltage drop in between the LDR and the potentiometer has exactly the same magnitude. And if you subtract the two, of course, the voltage difference between the 2 points is going to be 0. Let me insert this blue pin here, so we're not using the negative terminal of the battery now as a reference pin, but the point against which we want to compare the reference signal. If I now turn the knob, also you can see that we are able to generate a negative voltage here by using this approach. And once I turn the knob, you can see that the difference is getting smaller and smaller. Now approaching 0. It's very sensitive to touch here. Okay, we're somewhere in the vicinity around 0.01516 volts. And once I place my finger atop the LDR, you can see that the voltage increases. And if I increase the light value, if I make it brighter, you can see that the value is getting a negative sign, which means we get a value below 0. And this is just what we are looking for our operational amplifier, which we are now going to talk about. You can see the OPV here on this circuit board. We have already discussed this in another video, and this OPV here is what we will use to evaluate the signals between the LDR and potentiometer, as well as between this fixed value voltage divider here. Let's fire this one up here by first connecting the positive and negative terminal
of our battery to this board here as well. The LED, or not the LED, but the diode here is against polarity errors. If you by error connect the positive to the negative terminal and vice versa, and the LED will light up as soon as there is a positive voltage difference between the two entrances of the OPV. Now let's briefly discuss the components here. This is the OPV, this is the positive power supply, this is the negative power supply, the connector where the LED, where the resistor is connected to, this is the output, and this output also is connected, the output path also contains this lit up LED now, and these two here, these are the input pins, and as soon as there is a positive voltage difference between the two, the high gain of this OPV here leads to a saturation at the output, which is happening now due to minute differences between these two connectors. So even if no signal is connected, the very, very small differences of the voltage levels at these two pins here lead to the LED being lit up. And what we want to do now is we want to connect the both input pins of the OPV to the voltage levels between the LDR and the fixed value resistor voltage divider. Let's first connect the resistor voltage divider to one of the input pins. Let's use this one here, and as you can see now, the LED has gone out. Let's now connect the other one in the position below the LDR. Let's insert it into this one here again. And now let's have a look at what's actually happening here. If I now place my finger across the sensor, nothing happens. Let's turn the knob a little bit and see what happens. I think we have to adjust it slightly more. And what you can see now is a behavior which we intended to. What we now have done, we have calibrated this setup here, which is also called a Wheatstone bridge, by carefully adjusting the light level or the voltage level in between these two components here in such a way that for this ambient light which we currently have, the comparator is switched off, and as soon as the voltage, as soon as the light intensity decreases, for example by placing my finger across the LDR here, we get a positive voltage difference, which leads to the output of the OPV being fired up. And this is how you can use a sensor by connecting it to a double voltage divider, by comparing two voltage levels with an operational amplifier to trigger an output signal. And in one of the next videos, we will also connect this setup here not only to an LED. We will trigger a transistor-based switch, and this transistor-based switch is going to fire up this relay here, but this is only a sneak peek at one of the upcoming videos, which leads to an incandescent lamp being lit when this relay is triggered by the output of the OPV. And everything is going to be based on the signal which is amplified by this LDR here using an operational amplifier in the upcoming project.